They look so cool. These are called banded iron formations. These visually striking layers are often burnt orange, yellow, or silver and brown, and this is where we get all of our iron from. And according to brand new research, these iron formations may be responsible for some of the most explosive and widespread volcanic events in Earth's history. And banded iron formations are some of the oldest rocks that we have, forming billions to hundreds of millions of years ago. And these were created when rocks full of iron sank down to the bottom of the ocean, becoming stone. And in some brand new research, scientists have found links between the large igneous provinces, which are those massive volcanic events I just mentioned, and subducted formations of iron. Banded iron formations are chemical sediments which are precipitated directly in connection with seawater rich in dissolved iron. And metabolic actions of microorganisms with things like photosynthesis are thought to be drivers for these formations. And the largest deposits of these iron band formations occurred around 2.5 billion years ago during the Great Oxygenation Event. And we all know that the Earth is made of a series of plates which have moved over time. And during early Earth, there was a lot more ocean than there was continental crust, which means there was plenty of place for banded iron formations to be created. And due to the movements of plates, those oceans have opened and closed over time. And what the scientists are saying is when these oceans close due to the movement of these continental plates, a lot of the banded iron formations will get subducted into the mantle and even touching the outer core. And here's a great animation showing the movement of the plates over time. This is around the last 500 to 600 million years, but you can clearly see oceans are opening and closing and growing, continents are moving, which is why all these banded iron formations would have been deposited and then subducted beneath these continental plates. And because of their rich iron content, banded iron formations are more dense than the mantle, which means any plates that get subducted into the mantle will basically sink down to the bottom. And here's where this paper comes in. Because throughout Earth's history, we've had really large igneous provinces, which have literally changed the face of the Earth. They're so important for our evolutionary journey and the planetary evolutionary journey. I mean, here's an example of all the large igneous province bodies that have occurred throughout Earth's history. They cover most of the planet. And one of the questions scientists wanted to tackle was, is there a connection between plumes of magma which rise up and create these large igneous provinces and where they occur? And you may be asking, well, volcanics is just that, right? Like magma rises up through the crust and it creates a volcano. Yes, that's true, but they usually occur at convergent or divergent plate boundaries. So this is where either the crust is separating or coming together, so there are areas of weakness or where there's lots of pressure of magma building up. What's rarer, however, are hotspots. One example is Hawaii. This is an island arc, which you can see there. If I move it up, this is an island arc right here. And you can see that it's moving along with the plate. That's because there is a mantle plume feeding the volcano directly from the mantle without there being any plate boundaries. We call these intraplate hotspots. And the question is, why do they occur? What is so explosive and intrusive about these mantle plumes that come all the way down from the deep down under that reach the surface and essentially pierce through? And when the researchers have showed that under the right pressures and temperatures, banded iron formations will become extremely conductive. And researchers have found correlations between the timing of deposition for the banded iron formations and then later those igneous provinces being created. In one model, they proposed that these banded iron formations essentially become hot plates on the outer core where they convect and conduct heat in the mantle, which then creates these plumes because they're very, very conductive under high temperatures and high pressures. The second model they propose is it's not just the iron formations by themselves, but it's also the slabs of the plates which help push mantle towards those IFs or iron formations and then create the mantle plumes. And their model nicely predicts and explains why we get these igneous provinces in very random locations across the world. Most of them exist on the intraplate scale, which means they're not on any boundaries. And the researchers are looking to do more research into this area because these have great impacts on how the Earth has changed over time. And if we can understand how iron formations have influenced hotspots in the mantle, this can also be used for exoplanets in our planetary exploration exercises. Because with most things with geology, without planetary evolution, you will not get biological evolution. So iron is not just useful for humans. In fact, it may have played a more important role in Earth's history than we ever realized. I hope you enjoyed the video. Please like, share, comment, and follow, and I'll see you in the next one.